Hello everyone, welcome to my channel. My name is Rishabh and today we will be going to discuss about this very cool project, that is real-time 2D object recognition. So guys, you must have seen all these videos where let's suppose you take your camera and place it in front of an apple. It will recognize it and say that yes, this is an apple. This is a pen, this is a scissor. So in this video we will implement that whole project. And I assure you guys that you will learn a lot from this video. So let's move forward and see what we have to do. So in this project we will discuss about 2D object recognition, and our main goal will be to make the computer identify a specified set of object placed on a white surface, okay, in a translation, scale and rotation invariant manner from a camera that will be looking straight downwards. Here our computer will be able to recognize every single object placed in the image, and it will be able to identify the objects and output image. Okay, so moving forward, if we have to implement this project, we'll have to go step by step. And the first step will be to threshold the input video, where our task will be to implement a thresholding algorithm for a video to separate the objects from the background. This will create an object recognition system by applying the thresholding algorithm to each frame of the input video. By this, our algorithm should be able to identify and display the thresholded video where the objects they will appear as distinct from the background. So in this first function, this threshold function, it will first convert the image to grayscale, and then it will apply a thresholding operation where it will set any pixels with a value less than or equal to 130 as foreground, that will be white, and other pixels as background, that will be black. After that, the function will return the thresholded image as a grayscale. Once we are done with the thresholding, our task will be to clean the binary image. Here our main task will be to improve the quality of the thresholded binary image by applying some morphological filtering. So let me tell you what is morphological filtering. In morphological filtering, they basically modify the shape and structure of the image using some mathematical operations like dilation and erosion. So dilation, it basically expand or grows the region in any image, while the erosion, it shrinks or reduces them. And by selecting any appropriate strategies, we can effectively remove the noise, or we can remove any kind of blobs or fill the holes in the thresholded image. So this function will perform the cleanup. Okay, it will help to remove all the small noise and smooth the binary image. After that, we'll have to do the segmentation. Okay, so here our task is to implement connected component analysis on the thresholded image and the cleaned image to segment it into regions. Here the connected component analysis algorithm will identify distinct region in any image by grouping together pixels that are connected or are adjacent to each other. Okay, so here in this function we are directly using the OpenCV library. OpenCV library provides us a connected component function that can be used for this purpose, which also returns all the stats about the region. Okay, so if we see this this function, this get region function, this will extract the largest 3 regions from a given image. It will use the connected component labeling algorithm to label each pixel in the image with a unique region label. The function then calculates the area of each labeled region and select the largest 3 regions that meet a certain area threshold. After that, it will return an image where each region is colored with a random color, and it will update the top n label vectors with the label of the largest region. Once we are done with the segmentation, we will compute feature for each major region. Here our task will be to implement a function that will compute a set of features for a specific region in an image. This function will take a region map and a region ID as an input, and our goal will be to calculate features that are invariant to translation, rotation, scale, such as movement around the central axis of rotation. One of the features that we should be computing will be the axis of least central moment, which represents the direction of region's elongation. Another feature will be the what we say bounding box, oriented bounding box, which is the minimum bounding rectangle that encloses the region and is aligned with the region's orientation. OpenCV library basically provides us the function for computing moments, which will be used to calculate the features. To know more about moments, blobs, HU moments, contours, you can visit my GitHub profile and you can see this folder, that real-time 2D object recognition. You can read about all the minimum area, what is blob, what is the centroid of shape. You can learn about them from here in a very brief manner. Okay, so once we are done with this section, hereafter we can get the bounding box, we can draw the line, we can draw the bounding box, we can draw the HU moments, we can calculate the HU moments, then we can also calculate the Euclidean distance. After all this is done, we will have to collect the training data. Here our task will be to modify the system to have a training mode where it can collect feature vectors from objects and then associate them with labels or names. Okay, and it will then store them in the database. This will allows the user to gather feature vectors of known objects and save them for future use in classifying unknown objects. Okay, so to implement this, I have introduced a key press trigger, such as whenever I will press T, the system will prompt the user to enter a name or label for the current object. It will then capture the feature vector of the object and then it will store it in a file along with the corresponding label. After the training is done, we will classify the image. Here I have used two classification. Let's suppose whenever I will press N, it will find the nearest neighbor, and let's suppose if I use K, then it will use KNN classification. Okay, so in N, our task will be to enhance the system's capability to classify new feature vectors using a known object database. Here I have used scaled Euclidean distance metric for classification. After the classification is done, I have to evaluate the performance of our system. Okay, on multiple images of each object and create a confusion matrix to compare the true labels of the object with the labels that are assigned by the system. Once the confusion matrix is done, it will provide a summary of the classification results showing the number of correct and incorrect classification of each class. Okay, so this is the whole gist of this project, and so moving forward, let me show you the whole working of this project in real time. So first of all, I'll go to the folder where my project is kept. Okay, and now I will CMake. It is showing like this because I have already done this project. I have already trained my data. Okay, now I will make to see if there are any errors. After that, it will generate an executable with the name object recognizer in the bin folder. So I'll enter in the bin folder and see for it. Here in the green color is the executable, and this OBJDB is the database, the CSV file where all my training data is made. So now to run this, let's see the code. First I'll have to run it, and then in that I will have to enter my arguments. The first argument will be the path to the CSV, which is OBJDB, which I have already created, and then the second input will be the classifier. I will have to enter N for nearest neighbor and K for KNN. For this video I will be using only N. You can use K also and check if it is working or not. Let's go back again. So first I will enter ./obj, and then I will enter my first argument, that will be OBJDB part to the CSV, and then I will enter N, then enter. Okay, So now I have already trained my data, so that's why it is showing some random things. Now let's try to train our data on this glass. It is already showing, but see, it is also showing some errors because I have trained it for very less time, for let's suppose for 20 or 30 times. The number of time I will increase the training, the more accurate results it will produce. Okay, let's bring it in middle. Yeah. Okay. So we will have to take the video of this from every angle. We will have to train this from every angle possible. See, from every angle it is showing glasses because I think the training is done very properly here. I also trained my data for the speaker. See, it is showing errors. Some errors, sometimes it is showing speaker because I have trained it for very less time. I also trained it for trimmer. I also trained it for this mouse. Let's see, for my cap, it is showing it as speaker now. Yeah, hat. I also trained it for this scissor, but sometimes it will showing it as fork because they are very similar. I also trained it for this pen. Now let's suppose if I put all these three in one. It is not fitting here in one frame. Yeah, you can see how accurate results it is producing. Okay everyone, so that's all for today. In the end of this video, I would like to thank my professor, Professor Bruce Maxwell, under whom I did this project and I learned so many things. I hope you guys enjoyed this video. Thank you so much and have a nice day. Bye.